All right, in the second part of 3.3, we are going to take a look at synthetic division and the remainder theorem. So, synthetic division is just a shortcut for polynomial long division if the divisor is in the form of x minus some number. All right, so if the divisor is in any other form, we would have to use long division. Let's take a look at a few examples here. So, what I want to look at first is the divisor. It is in the form of x minus a, so I can use synthetic division. Now, the first thing we want to think about is if I set that equal to 0 and solve, we would get a value of 3, right? So, the first thing I'm going to do to set up synthetic division is put that 3 in a little box here. Then I am going to list out all of the coefficients of my numerator or of my dividend. So that'll be 2, 1, and 6. So now the process, bring this first number straight down beneath this bar that we just drew, and then multiply that number times whatever number is in my box. So 2 times 3 is 6, and then that value goes right here. And then we add down. So 1 plus 6 is 7. Then we repeat the process. So 7 times 3 is 21. That'll go here. And we add 6 plus 21 is 27. Now, I'm going to box up this last number because what we have just created is the quotient. Now, the quotient, or I should say the coefficients for the quotient. The quotient is always going to be a power that is 1 less than what we started with. So we started with a second degree polynomial here. That means that this first coefficient is the coefficient on a first degree term. So this quotient would be 2x plus 7, and then my remainder is 27. So remember, the way that we wrote a remainder was like this, just putting it over the divisor. So this is equal to 2x plus 7 plus 27 over x minus 3. Okay? Let's look at another example. So on this one, again, first step, look at the denominator and think about setting it equal to 0 and solving. Okay, you don't have to write that step down. All right, so if we did that, we would get 2. Then I want to list out the coefficients of my numerator. So that'll be 1, -2, 3, and -6. So the process, bring this first number straight down, then multiply. 1 times 2 would get me 2. Then add -2 plus 2 is 0. 0 times 2 would be 0. 3 plus 0 would be 3. And then 3 times 2 is 6. -6 plus 6 is 0. So in this case, we have a remainder of 0. Now, since I started with a third degree polynomial, that means my quotient is going to be second degree. So this is the coefficient of my second degree term. So we'll have 1x squared plus 0x plus 3. And then my remainder is 0. So this would all just be equal to x squared plus 3. All right? And then remember, another thing that we talked about in the last video was I could also rewrite this then as x cubed minus 2x squared plus 3x minus 6 equals x minus 2 times x squared plus 3. Okay? We have essentially used division to factor the polynomial. Okay? Let's do one more example here. So, same idea. If I set my divisor equal to 0 and solve, I would get -1. And then listing out the coefficients, I would have 2. Now, just like when we did long division, we have to be careful. If we are missing a term, when we were thinking about going in sequential order of exponents, so I do not have an x cubed term here. We need to put in a 0 placeholder. just like we did for long division. So my coefficients will be 2, 0, -3, 5, and 17. So let's go through the process. Bring that first number straight down. Multiply. 2 times -1 is -2. 0 plus -2 is -2. -2 times -1 would be +2. -3 plus 2 would be -1. -1 times -1 would be 1. 5 plus 1 is 6. 6 times -1 is -6. And 17 plus -6 would be 11. So my answer, since I started with a fourth degree polynomial, this will be a third degree polynomial. So we'll have 2x cubed minus 2x squared minus 1x plus 6, and then 11 is my remainder. So we write our remainder as a fraction over the divisor. Right? So this would be my answer for this problem. All right? Now, remember, if the remainder is 0, then x minus a is a factor of my polynomial. And that occurred in our second example here, right? Where we just got x squared plus 3 and we were able to rewrite this in factored form. All right, and there's lots of other ways to say this, right? Then we could say something like that a value is a 0 or a solution or an x-intercept, okay? So let's take that into the remainder theorem then. Right? So the remainder theorem says if a polynomial is divided by x minus a, then the remainder is just whatever we would get if we plugged that value into the function. So let's illustrate that idea here. So let's say here's our original polynomial, and I want to start by dividing by x minus 1 and finding the remainder. So we can use synthetic division for that, since we have x, our divisor is in the form of x minus a. So if I were to set this equal to 0 and solve, I would get positive 1. So then I'm just going to list out my coefficients. So 2, and then we do not have an x to the fourth term, so we need to make sure we put in a 0. Then -4, 5, -7, and 2. So bring the first number straight down. 1 times 2 is 2. Add. 1 times 2 is 2. Add. 1 times -2 is -2. Add. 1 times 3 is 3. Add. And 1 times -4 is -4. And we are just left with -2. So what this is saying is that if I just plugged -2 into the function, or I'm sorry, if I plugged 1 into the function, I would get out -2. Right? That's what this remainder theorem says. So let's actually illustrate that in part B here. So f of 1 just means I'm plugging 1 in everywhere I see an x. So 2 times 1 to the 5th minus 4 times 1 cubed plus 5 times 1 squared minus 7 times 1 plus 2. So that'll just be 2 minus 4 plus 5 minus 7 plus 2. So 2 minus 4 is -2, plus 5 would be 3, minus 7 would be -4, plus 2 would be -2. Okay, so we got the exact same thing by plugging in 1 as we did for the remainder when we did synthetic division. That's not a coincidence. That happens every single time. So the remainder in synthetic division is the exact same as if I were to plug this value into the function. Right? It's a pretty neat little trick, and it's something that you can use. Right? If we have an ugly polynomial, right, we can use synthetic division to fairly quickly calculate this value. All right. Now, part C says, is 1 a root of this polynomial? Well, the answer would be no, because the remainder when we divided was not 0. Okay? In order for this to be a root or a solution or an x-intercept, we need the remainder to be 0. So part C, the answer is no. We can just say remainder is not 0. Okay, so the last idea then is that kind of just what we talked about, right? A polynomial is a factor if and only if f of a equals 0. So we want to know, is x plus 3 a factor of x to the 5th plus 3x to the 4th plus x squared plus 8x plus 15? There's actually two ways that we could go about doing this. Okay, the first would be to just plug -3 into the function and see if we get 0. So let's do it that way, right? Let's say f of -3 will be -3 to the 5th power plus 3 times -3 to the 4th plus -3 squared plus 8 times -3 plus 15. That looks pretty ugly to try to calculate that, okay? This is a situation where it may actually be easier to use synthetic division, all right? So I'm actually going to do that here, right? So my coefficients would be 1, 3, 1, 8, 15, right? Oh, I forgot a 0, didn't I? 0x cubed, so that will go right here. So 1, 3, 0, 1. All right, so bring the 1 straight down. Multiply 1 times -3. Add, multiply, add, multiply, add, multiply, add, multiply, add. I think that was a lot quicker than trying to go through and evaluate this. Okay? We end up getting a remainder of 0. If we were to calculate this all out, we would actually find that this is equal to 0. Okay? That means that x plus 3 is a factor. Right? We're going to look at this a lot more in the next section. Right? But for now, I want to make sure that we understand what this means. One final example here just says show that 2 is a 0 of this function, and then go one step further and use the depressed polynomial to solve for all zeros. All right, so let's see what that means. Okay, so first, we want to use synthetic division to show that 2 is a 0 of this function. So I'm going to list out my coefficients: 3, 2, -19, and 6. So bring the 3 straight down, multiply, add, multiply, add, multiply, and add, and we get a remainder of 0. So since we started with a third degree polynomial, my new polynomial will start with an x squared. Right? This is called the depressed polynomial. Plus 8x minus 3. So now, to solve for the rest of the zeros, I just want to take this quadratic and solve. Right? There's a few different ways that we can solve a quadratic. If we can, we could try to factor, right? Or we could use the quadratic formula. We know the quadratic formula would work every single time, so let's use that. Quadratic formula is x equals opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, 3 is my a, 8 is my b, and negative 3 is my c. So plugging all that in, I would have negative 8 plus or minus the square root of 8 squared minus 4 times 3 times negative 3 all over 2 times 3. So let's simplify. We get negative 8 plus or minus. So 8 squared is 64. And then negative 4 times 3 would be 12 times 3 would be 36. So this will be plus 36 all over 6. So negative 8 plus or minus. This would end up being 100, right? The square root of 100 all over 6. So we end up getting negative 8 plus or minus 10 over 6, right? And we can then split that up into the two options that would create. We would have negative 8 plus 10 over 6 and negative 8 minus 10 over 6. So negative 8 plus 10 would be 2 over 6, which would reduce to 1/3. And negative 8 minus 10 would be negative 18 over 6, which would just be negative 3. Okay, now we could have actually factored this polynomial, okay, but I just chose to use quadratic formula. Just we have those options. So what this means, okay, we have 3 solutions for this problem. The first was 0, and then we also have 1/3 and negative 3. So my answer is all of those. X equals 2, 1/3, and negative 3. We're going to do a lot more problems like this in the next section. All right, so that is it for this video. The final question is going to pop up asking you what questions you have.